everyone. This lecture will serve as an introduction to our bedrock mapping project at Matthiessen State Park, Illinois. First off, where are we going? We're heading straight west on 80, which is a toll road, so be warned, for about 100 miles past the town of Ottawa to Utica, Illinois, and then south. So it should take just under 2 hours to get there. As you can see, between the towns of Ottawa and North Utica along the Illinois River, we have three really special places. We have Buffalo Rock State Park, we have the Starved Rock Nature Preserve, and then if you head just a little bit south, where we have the Vermilion River coming down from the Illinois River, there's Matthiessen State Park. And that's where we're going to be doing this particular project. So there are really interesting things to see out in this area. So one of the most striking things when you come from the flatlands is that when you get out to this area, you see these towering bluffs. They're very intricately eroded, so we can look at weathering patterns in different types of rock, and maybe you can guess what type of rock is shown here in the picture in the center, and then also with the waterfalls. We can also see the contacts between multiple rock units from the Ordovician and Pennsylvanian, and we can also see rocks with different orientations. This is an area that is kind of the fuel for many different field trips. So here is just a sampling of some of the guides from field trips that have been taken to the area. This reading on the bottom left, Time Talks, is kind of just a user-friendly guide for the public, but has some really great information about the geology, plus some really nice digital elevation models in it. And then these other ones are produced by Illinois State Survey and also by the Clay Mineral Society as well. So what do we want to practice when we get out there? We want to practice identifying and describing different rock types in detail. We want to practice using stratigraphic columns. We want to practice identifying contacts, and Stephen over here is kind of showing us that by standing on a contact. We want to practice measuring strike and dip of different rock units, and then we want to take this information and put it onto a topographic base map. So by now you've probably worked with stratigraphic columns, or just the principle and idea of stratigraphy. Stratigraphy is the order and relative position of strata and their relationship to the geologic timescale. So on the left here, I have the stratigraphic column for the state of Illinois, so not this particular area. Now to build a stratigraphic column, or even to understand stratigraphic relationships between rocks that you see in the field, there's a couple of things that you have to do. You have to be able to identify and describe different rock types and rock units. You need to be able to locate contacts if you can and determine the thickness of units, and then also be able to interpret the age of rocks and represent them on your stratigraphic column with appropriate symbology. So again, if we look at this particular stratigraphic column, what can we learn about the state of Illinois? So here we have the bedrock map of Illinois, and if you look at this, you can see again different types of rocks. Sandstones, I see, dolomite, limestones. So what kind of depositional environment is jumping out to you when I talk about these types of rocks? You can also see some of the ages, fairly good representation here in the Paleozoic. Okay, then we get up into the Mesozoic. We have some Cretaceous rocks. And we're going to look a little closer to the stratigraphic column for our study area in particular. But as you look at the state of Illinois, by now you've probably figured out that a lot of this is sedimentary rocks, largely consistent with what we see in Indiana. And take a look at the symbology that you see here in the stratigraphic column, right? Alternating sandstones, shales, limestones, and dolostones. Now, another important aspect of Illinois geology, again, just like in Indiana, is we have our bedrock, and then we have kind of a jump forward to the quaternary deposits that are associated with the Pleistocene glaciations. We can see in the south and in the west some pre-Illinois glacial deposits, but really the majority of Illinois is covered with the Illinois glacial deposits, and then a really nice sequence of moraines associated with the Wisconsin glaciation and, of course, the retreat as well. And in between, we see a lot of the wind and river deposits that are associated actually with ancestral Lake Michigan as we breached these moraines to create the waterways that go to the Mississippi River. So I want to focus you on, again, the broad strokes of this stratigraphic column, but let's look at our times of interest. Okay, we're going to look at the Ordovician, Pennsylvanian, and the Quaternary. So here you can see for the Ordovician, I like this stratigraphic column because it gives us kind of the variable thickness as well. Not all strat columns will do that. It also gives us the age in the center in millions of years ago. And we have, for the Ordovician, largely dolomite and limestones with some sandstone, shales, and siltstones. So what do you think was going on in the geologic history to create that type of sequence of deposits? Notice now that we actually jump to the Pennsylvanian, quite variable in thickness. A note here tells us this is really important because remember, we're getting during the Pennsylvanian a lot of terrestrial plant development, and so coal deposits become really important in the geologic record of Illinois. We have largely shale and sandstone with beds of coal, limestone, and clay. And again, you can see from the strat column with the symbols here, and maybe you're comfortable with your symbols, maybe you're still learning, but you can see that there is quite a bit of back and forth between our shales, our coal seams right here, some sandstone lenses there, and then kind of some thinner beds of limestones as well. Now I again jump to the quaternary or quaternary, I like to actually say quaternary, and you can see that we have our diamictons or our glacial tills, lots of glacial outwash, gravel, sand, silt, lake deposits of clay and silt, wind deposits of loess and sand dunes, and there's a little note here that deposits cover nearly all of the state except the northwest corner and the southern tip. And then, of course, jump to today in the Holocene, and we have deposition of alluvium along those river channels. So now we're looking at a more detailed stratigraphic column of our actual starved rock area, okay, which includes Matthiessen. And now we're getting into not only the group, but down to the formation as well. So if you look at this one, which units of geologic time are represented by the rocks preserved in our area? Well, once again, we can see that there's definitely Ordovician, maybe some Silurian, we won't see them on the trip, Pennsylvanian, and then again we jump up to the Quaternary. Okay, so again we've gone from the group in this down to the formation. So some of the rocks that we're going to see are down here in the Ansel, Galena, Platteville groups. And there are several U's in this, which represents the term unconformity. So do you remember what an unconformity is? Okay, let's review that quickly because it's going to be important as we try to reconstruct geologic history. Simply stated, an unconformity is a gap in the geologic time caused by erosion or non-deposition. So it's a gap in the rock record. Okay, there are three major types. One is the disconformity, always the hardest to kind of identify in the field because you see these horizontal units remain relatively parallel. There's no dark wavy line when you're out in the field. So you really, if you think that maybe you have a jump in time between parallel rock layers, maybe you figure that out because there's a sudden transition between actual rock types. But you will have to take that information and go back to your stratigraphic column to kind of figure that out. Right? If you were doing this as an original study, you would have to find a tool to actually date those rock units. Angular unconformities seem to always be the easiest. Your underlying rock units have been tilted by some tectonic force, and then they've been eroded to ground level horizontally, and then horizontal deposition of parallel beds again initiated. Okay, so pretty easy to see in the field by the contact between the tilted rocks and the overlying horizontal units. And then a nonconformity is an unconformity between younger sedimentary rocks and then crystalline rocks beneath. Here are some nice examples. Angular unconformity. Another one, maybe hard to see in the field. You can see that there's a contact, but again, you'd have to go back and you would have to find the age of some of these rocks. But we have a granite that is, again, overlain by a sandstone. All right, so a nonconformity. So let's look specifically at the rocks that we're going to see in the field. Here are some of the units that we're going to see. We're going to see the Shakopee. And what type of rock is this? It's a dolomite. Again, dolomite is the term usually used for the mineral itself. Dolostone is what we call it when it's actually in a rock unit. And you can see the symbology here. It looks like limestone, but again, it's got these tilted lines. Okay? And so we see the Shakopee, we see the St. Peter's sandstone, which this is a famous rock around the world because of its purity, its uniform grain size, and it is mined quite extensively, or it would be if it wasn't protected, because of its high quartz content. Then we get into the group, the Galena Platteville, and this is a series of dolomite, limestones, and these are kind of stand out because they're slightly cherty. Then we're going, not on this trip, but in the area we also have the Pennsylvanian Bund Formation, and that's a series of limestones, again, kind of an argillaceous limestone. And then we have our quaternary deposits, which are going to be till and outwash of the Illinois and the Wisconsin. So before we go too far, kind of think about these types of rocks. What type of rock, igneous, metamorphic, or sedimentary, do we have here? And what do they tell us about the geologic history of the area and the depositional environments? Hopefully, you said that you can imagine yourself on the edge of a shallow marine coast. All right, so when we hear about limestones, we should be thinking shallow marine, especially if we start to see some of those shallow marine fossils. Maybe barrier islands, because we'll have sand moving along a shallow coast. Estuaries, maybe where we have still water and we're starting to accumulate some of our fines, that would eventually become a shale. Tidal flats, again, same kind of thing. The swamps would be where we find which rock? Right, we would find the raw materials to form coal in a swamp. And then, of course, we have the sandy deposits of beaches. And we may even have reef deposits as well. So as we zoom in on the rocks that we have in our area, in this particular study site, we're really going to be looking at St. Peter sandstone and then getting into our Platteville limestones. But we can look also to the older Shakopee as well. And we can start thinking back to the marine transgression that we've seen, right? The marine transgression tells us that we sort of have this environment where we may have alternating limestones, which could later, through replacement, become the dolostones. We're going to have shales. We're going to have sands as well. So this is the type of environment along a coast with a fluctuating water level that may be leading to a sequence of rocks that we see in this location during the Ordovician. So we jump from that study area stratigraphic column that gives us some loose information and kind of points us to the fact that we have several unconformities in the area, to the much more detailed stratigraphic column that we're familiar with in the more recent publications, and we can actually get down to the group level and looking at the different thicknesses of these rocks. And so once again, take a little bit of time to review the symbology with the different rocks, the glacial drift diamicton, the limestones, and again some of those characteristics. Are they cherty? Are they sandy? Are they argillaceous or shaly? The dolostone, sandstone, and again some of the detailed symbology, and then our shales. And coal, which we won't be seeing on this particular trip out there, is just represented by those dark lines. But this is a much more detailed stratigraphic column because you can see the thicknesses in our study area as well. So let's look at using those paleo maps from Scotese what was actually happening during the Ordovician. So this is a picture of the middle Ordovician, and you can see what's happening where Illinois is today. I love that they added this little outline of the Great Lakes so we always know where we're at. But you can see this is relatively shallow marine environment located near the equator. So backing up a little bit to about 485 million years ago, and these are just happen to be kind of the windows of time that are represented by the paleo maps. So during the Ordovician, northern Illinois was part of a broad upland that was undergoing extensive erosion. Erosion wore the land down to near sea level, and it forms a wide platform submerged multiple times by submerged and exposed multiple times by fluctuating sea levels. And that platform is called a peneplain. And so in this diagram, they actually show the darker, deeper waters with the darker blue, shallow waters with the white, and then when it becomes land, it may be sort of a light yellowish if it's right along the shoreline, or solid land, as you see here, is represented in a darker brown. So we can kind of look at a couple of other images, but we have this Epiric Sea, which is this kind of inland sea that is fluctuating back and forth. And again, we're on a really shallow platform, so small changes in sea level are going to make big changes as far as inundation of the landscape. So about 485 million years ago, you can see that our study area is going to be kind of in this deeper water. By about 470 million years ago, it is shallower. We're even seeing some land. Okay, so very shallow again. And then bringing us back to the middle Ordovician. So I just want you to have this impression of our study area as being on this really shallow coast where these fluctuating water levels are going to change whether you're in sort of a deep marine, shallow marine, or even in a coastal environment. And don't forget, the Ordovician world was really exciting. I love this picture from the Illinois State Museum, a really great exhibit, but a nice explosion of marine fossils that we can look for in some of our rocks. Now when we get into the Pennsylvanian, which we mentioned are also represented here, we again have a jump in time, don't we? So we can see here that we are in the early Carboniferous, so Pennsylvania is part of the Carboniferous, but again you can see that we are once again submerged as part of that as well. But a lot of fluctuations in water level during that time as we're actually starting to build the Appalachian Mountains to the east. All right, so a big jump now to what's represented in our study area, the last glacial maximum. So again, most of our glacial record is going to be from kind of pre-Illinoian even though there were several fluctuations or advances and retreats of the ice sheet, kind of gets lumped together because a lot of the record is kind of smushed, if that's a great way to say it. So we can really discern Illinoisan deposits and Wisconsin deposits, but it's harder once you try to get a little farther back in the Pleistocene. But what an amazing record. Okay, so we have these extensive morainal deposits, and they really map out kind of the retreat of the edge of the Laurentide ice sheet. Up here we have ancestral Lake Michigan. So one of the things that's really important is that we were getting damming of waters behind these end moraines. Okay, so you can see in this diagram, a little hard to see, an ancestral Lake Ottawa, which was dammed up behind some of these moraines, and a Lake Pontiac. So kind of when they got dammed up, we give them unique names. All right, but also the same thing as we have the Chicago outlet as well. And as Glacial Isostasy was operating in the region after the retreat of the Laurentide ice sheet, eventually the water breached the moraines and we developed the Chicago outlet. Big, massive floods of water. Also, the same type of glacial damming happened with these Lake Pontiacs and Lake Ottawa. And so that was kind of the mechanism that ripped open these areas leading to the Illinois River that we see today, and then these high bluffs. Okay, so we eroded away a lot of material, down cutting because of these rapid torrents of water that were released after the glacial damming. In our study area, we're going to be kind of right along the edge of the Farm Ridge moraine, and the little green areas are the parks, and Matthiessen is here along this Vermilion River, okay, which is coming down. I shouldn't use those terms because we're showing the direction of flow is actually going to the north to meet up with the Illinois River and then discharge and head down to the Mississippi River as well. Okay, so that's a lot of the background of the area, but what are we going to do out there? Our goals are actually going to be pretty simple, and we're only going to stay in that Matthiessen State Park area. We're going to need to locate ourselves on a topographic map. We're going to need to measure and estimate horizontal and vertical changes that we see in the canyon and represent those on a topographic map. We're going to need to identify our different types of rocks, place them in the context of our local stratigraphic column, and identify contacts. We're going to need to measure rock orientation using some strike and dip and also represent that on our map. And we're going to need to place all that information onto the topographic base map. So Stephen again is kind of showing us one of our really remarkable sites. This is along the Vermilion River. Okay, and we are looking downstream in this image, but you can see that something is definitely different about this rock unit, right? We have tilting. So this is where we're going to be able to really nicely measure strike and dip. When we're taking strike and dip, we're going to need to know the strike direction. Let's look at this diagram. The strike is going to be that cardinal direction, the north, south, east, west, but we're going to be a little more sophisticated and we're going to put that in the context of our azimuth or 360 degrees. So it's good to imagine that your study area fills up with water, and that contact line of the horizontal surface is going to be what we call our strike. Our dip is going to be that difference in the horizontal plane to the actual surface of the rock unit. And we're going to represent that on our maps by having the strike with a longer line, and we need to do a little line making kind of an exaggerated T. But the shorter line is going to be represented in the direction that the rock is dipping, and we always do it at a 90-degree angle. So we're going to dip downhill, and then you're going to actually place the little number, which tells us the actual dip that you measured from the horizontal. So with this little symbol, we get our direction of strike, which really kind of goes in two directions, right? Because it's a line. but we measure it relative to north. So our direction of strike and then our direction and angle of dip. To do that, we're going to be practicing with our Brunton compass. More recently, people have also been using another tool called a Silva. One of the reasons why people use the Silva is because it's about $300 cheaper than the Brunton, but the Brunton is basically the tried and true tool of geologists. So that's what we're going to be using this time out. It will give us the information we need. It will help us measure strike and dip, like you see this person doing here. And it will also help us establish the direction of our strike angle according to, we'll use the azimuth. This is for you to review. It kind of gives you the different parts of the Brunton, and we will look at this more in the field. Before we even get started, we have to set any angle of magnetic declination to for our study area. What's interesting about our study area is it is exactly the same magnitude, but in the opposite direction of the magnetic uh, declination that we have at IU Northwest. So that's always kind of fun and a little confusing in the field. So again, take a moment to review these parts of the Brunton. All right, so again, in the field, we're going to practice going ahead and taking our measurements of strike and dip. We'll review this right hand rule, and that means if you're in the field and you use your right hand, you want to have it so that the fingers of your right hand are pointing down the dip and then your thumb points in the direction of strike. So we want to do this so that we are representing our dip in the right way relative to our strike. Also, we're going to be using azimuth, which means that we want to know our directions not just by north, northeast, but we want to know them in actual angles relative to north. And we do that in 360 degrees going to the east. So you can see in this example that our strike measurement is 37 degrees, okay, from north. But again, it's a line, so that is also the same as saying 217 degrees. Either one will get you to the right place. I always like to just think about it as the easiest and smallest angle from north. And then dip again has to be represented at 90 degrees to that with a small line, and you just write the angle that you measure. And then finally, this is not our map, but it's another example of how we're going to take our observations and we're going to overlay them onto the topographic base map. So we want to try to, in the field, estimate both our vertical and horizontal changes correctly. And then at the end here, I've just placed some definitions for the different rock types so that maybe you want to review these if you are a little out of practice. All right, so now you have a strong overview of what we are setting out to do and a little bit more information about our study area.